before I formally introduce our honored speaker today, we are also honored for the opening by President Yang of NTU. So I invite President Yang first to the podium.
Professor Kajita, distinguished guests, colleagues, ladies and gentlemen, it's really my great pleasure and honor to say a few words for the opening of the Professor Kajita's colloquium today. I would like to thank Professor Kajita because Professor Ho mentioned to me, actually, he contacted you before the announcement of the Nobel Prize winner in physics 2015, and Professor Kajita kept his promise, although he is very busy after the announcement of the winning of the Nobel Prize in 2015, but he still kept his promise and came to NTU. This is our greatest honor, and I would like to express my greatest appreciation to Professor Kajita. Professor Ho will chair your talk, and I'd like to invite Professor Ho to chair your speech, please.
So this is indeed a very unusual setting to get a Nobel Prize winner fresh off the press, right? So let me not go back to the history of the invitation, but maybe I just try to first say that we have two separate sessions. I would like to keep this first as a scientific session, although it's a colloquium. And then we'll have a break and then go towards a press Q&A. Okay, so let me start the introduction. Professor Takaaki Kajita, or Kajita Takaaki, 尾田隆章所长 of Tokyo University is our honored guest today. Professor Kajita received his PhD from Tokyo University in 1986. Actually, his thesis topic was on proton decay. But he shortly, actually I think beforehand, he switched to atmospheric neutrino studies with the Kamioka detector that he's going to introduce to us. So from 86 to 92, for 6 years, even Kajita-san had to work as a research associate. First at ICEPP, that's the Center for Experimental Particle Physics at University of Tokyo, and also at ICRR, which he stayed on ever since, the Institute for Cosmic Ray Research of Tokyo University. So in 92, he became associate professor, and in 99, he turned full professor, and also became the director of the Research Center for Cosmic Neutrinos, something that he holds to this day. And in 2008, he became the director of ICRR itself. So the conference that I invited Kajita-san to come is called ICRC. So you can see the close connection. And Japan really has a very strong tradition in this. Now, I think there are numerous prizes that Kajita-sensei has received. So I'll not mention the ones that are not truly personal. Super-K has received many prizes. So he received, in 1999, the Nishina Memorial Prize. And in 2002, I think a very nice prize from APS, American Physical Society, is the Panofsky Prize. And I think that's probably particularly memorable because he received it both with Koshiba-sensei and Tosuka-sensei. Both are his dear mentors. And I think that Tosuka-sensei, well, Koshiba-sensei received the Nobel Prize that year. Totsuka-sensei is, I think in Chinese, is like 大师兄, so the big disciple of Koshiba-sensei. So it's both like a colleague, you know, shi xiong, and also like a mentor, a teacher to Kajita-sensei. So I think that's particularly memorable. Because I think one thing I'm sure that Kajita-san would introduce to us as well, Totsuka-sensei passed away in 2008. So in 2010, when the first Yoji Totsuka Prize was established, guess what? Kajita-san is the first recipient, okay? So 2012, he was awarded the Japan Academy Award or Academy Prize, and 2013, the Julius West Award. Now, show off my German, the Julius West Prize, okay? And then, we zip to now, actually very peculiarly because the 2016 Breakthrough Prize in Fundamental Physics was awarded this year to 7 named persons of 5 neutrino-related experiments, but also more than 1,000 other people in these collaborations. So therefore, the highlight, all those cannot compare, and also our honor, our deep honor, like our president said, that after the Nobel Prize, 10 days after Stockholm, he's here with us. So, Kajita Sensei, I give the floor to you.
Well, first of all, I'd like to thank the invitation, also the kind words, Professor Yang and Professor Ho. Thank you very much. Now, I want to discuss the atmospheric neutrino studies and neutrino oscillations. Okay. This is the outline of this talk today. Well, okay, because I think many of you are actually not particle physicists, I guess. Therefore, I decided to discuss the physics of the discovery of neutrino oscillations, assuming that most of you are not the specialist in this field. So, first, I'm going to discuss just introduction, that is the Kamiokande, and which is the starting point of my research. Then I want to discuss the discovery of neutrino oscillation. Well, first of all, I want to mention about the history towards the discovery. Then I want to discuss the discovery of neutrino oscillations. And actually, that was more than 15 years ago. Therefore, I want to mention the recent progress, recent results. And before concluding, I want to mention about the future possibilities. And I'll summarize. Okay, now, introduction. As an introduction, I want to describe the Kamiokande experiment. Well, now, if we recall, say, 30, 40 years ago, there was a new theories. They are called grand unified theories. And these theories try to unify strong, weak, and electromagnetic interactions. And well, this is a particularly an appealing theory. Therefore, people would like to confirm the direct prediction of these theories. And one of the most direct prediction to be checked was the proton decay. In these experiments, in these theories, the lifetime of protons is expected or calculated to be 10 to 30 years, with the uncertainty of the order of 2 orders of magnitude. So, well, of course, 10 to 30 years is a long number, big number. Our universe is, the age of our universe is only 10 to 10 years. So compared with the age of the universe, the proton life is predicted to be 20 orders of magnitude longer. However, if we have 10 to 30 protons, and if we observe these protons for a year, we expect 1 proton to decay. So several people decided to search for proton decays, and these are the main experiments carried out in the early 90s. One was Kamiokande experiment, another one was IMB experiment, Muset produced. And these experiments observed many background events to proton decay that they contained atmospheric neutrino events. Okay, and this is the one of the experiments, Kamiokande. It is a 3 kiloton water Cherenkov detector, and the fiducial mass to search for proton decay was about 1 kiloton. So the detector itself is sensitive to proton decay if the lifetime of proton is shorter than 10 to 32 years. And well, okay, this photo was taken in early summer of 1983. Well, okay, before discussing the physics, I want to tell you what we have been doing during that period. This particular photo was taken in the spring of 1983. At that time, the Kamiokande group or team has been constructing the Kamiokande detector in the mine. So this photo was taken before going into the mine or underground. And well, and this is kind of typical number of people working in a day for the construction. And well, you can see here is Professor Koshiba, who is my supervisor, and also he's the 2002 Nobel Prize winner in physics. Also, here is Professor Totsuka, and he had been helping us from the beginning of the Kamiokande experiment, and later he took over the spokesperson of Kamiokande, and then also he contributed to Super-Kamiokande as the spokesperson. And well, behind these two giant people, there are, say, 4 students, 2 to 3 meters behind. And one of them was me. Okay, now, so anyway, we had the Kamiokande detector and tried to observe proton decays. And in fact, as already introduced, the topic of my thesis was proton decay. Okay, this is the copy of my thesis. In fact, I got PhD in March 1986 based on the search for proton decay. Well, of course, or unfortunately, or whatever, I didn't find any evidence for proton decay. However, during writing my thesis, I felt that the analysis software, including the particle identification, that is the separation of electron-like events and muon-like events, for the multi-Cherenkov event was not good enough to extract all the information that Kamiokande recorded. Oh, by the way, from now on, for the particle identification, I sometimes simply say PID. Anyway, one of the new software was the new particle identification software for multi-Cherenkov ring events. Namely, I designed that the particle ID software can identify if a Cherenkov ring in a multi-ring event, something like that, well, if the I just wanted to to know if each Cherenkov ring in an event is due to an electron or a muon. That was what I intended to improve. Anyway, you may notice that this is not the simple event to really know if the particular Cherenkov ring is due to an electron or a muon. So, of course, you have to start from the simplest application. That was for single Cherenkov ring. Well, compared with the event pattern in the previous page, the event pattern shown here are much simpler. You can see only single Cherenkov ring for these events. Therefore, we would like to know if this particular event with a single Cherenkov ring is due to an electron event or a muon event. Actually, the separation of electron and the muon is quite simple. An electron, if produced in the water, then it generates electromagnetic shower, and therefore the event pattern is kind of diffuse. On the other hand, muon just propagate in the air, in the water, almost straightly. Therefore, the Cherenkov ring has a much clearer pattern compared with the electron. Therefore, we wanted to use this feature to separate electron event and muon event. And of course, these electron events are produced by electron-neutrino events, electron-neutrino interactions, and these muon-neutrinos are produced by muon-neutrino interactions. So, by using these separations, you can simply count the number of electron-neutrino interactions and the muon-neutrino interactions. So, I try to check my particle ID program. First of all, the software was applied to the atmospheric neutrino Monte Carlo simulation events, not the real data, simulation events. And I confirmed that it worked well for them. Then the new particle ID program was applied to the real atmospheric neutrino events, single ring events. Then immediately we found that the result was strange. The number of muon-like events was much fewer than expected. Okay, I first thought that our Monte Carlo simulation might be too simple, and the Monte Carlo detector simulation did not reproduce the real detector. Anyway, I wanted to identify what is different between the real events and the Monte Carlo simulation events. So I decided to scan the real events in order to really know what's wrong. So I scanned, and immediately I found that the program, particle ID program for the real data were correct. well, that was actually in the fall of '86. So, well, Kamiokande had been taking data since '83. We have been scanning a lot of events. Therefore, well, our eye was trained very well. So, well, we were able to tell if an event is due to nu-E interaction or a muon-neutrino interaction. So we had the confidence to our eye. So, okay, now it seems that the particle ID result is correct. But, well, okay, maybe something might be happening in neutrinos. However, well, at that time, I was only half a year after getting my PhD. Well, if I make mistake at this early stage, my career may be a problem. So I have to be very careful. So I thought that it is much more likely that I made some mistake somewhere in the Monte Carlo simulation, data reduction, and or maybe event reconstruction somewhere. So we decided to check everything in late '86. Oh, okay. Okay, well, maybe I mishandled the slide. Anyway, okay, I follow the slide. Okay, now before going into detail of the analysis we carried out, I mentioned the what are atmospheric neutrinos. And here you can see the picture of the Earth. And here you can see the atmosphere. And in there, well, cosmic ray particles are coming into the atmosphere and interact at the top of the atmosphere and produces pions. And then these pions decay to muons, and then muons decay to electrons. And during this decay chain, 2 muon neutrinos and 1 electron neutrino is produced. So this is what we are observing. I tell you that for 1 pions, there are 2 muon neutrinos and 1 electron neutrino. In fact, this feature is very important. If we know this mechanism, then we naively expect that, well, mu to E ratio, nu mu to nu E ratio should be around 2. In fact, this naive expectation seems to be correct, even if we carry out the very detailed calculation. And this is the result from various calculations. And in fact, the flux ratio nu mu over nu E is around 2, as expected by this naive picture. So this is an important point that you should not forget about. Now, anyway, starting in late 1986, we started the various checks to find out what is wrong. And after a year of studies, we concluded that the muon deficit cannot be due to any major problem in the data analysis nor in the Monte Carlo simulation. So we think we did everything we should do. Then, of course, the next thing is to publish the data. In fact, this result was published in 1988. In fact, the essence of the paper is quite simple. We have two observation numbers, number of charged current electron neutrino events and charged current muon neutrino events, compared with the predicted numbers. So you immediately notice that the number of electron neutrino events are in good agreement with the prediction. However, the number of muon-like events has a huge deficit compared with the prediction. So anyway, that's the main result, and we concluded that we are unable to explain the data as a result of the systematic detector effect or uncertainties in the atmospheric neutrino fluxes. Some as yet unaccounted for physics, such as neutrino oscillations, might explain the data. Okay, that's our first paper on neutrino or atmospheric neutrinos. Now, here we wrote neutrino oscillations. Before going into the next stage, I want to tell you a little bit about the neutrino oscillations. Well, I'm sorry, I cannot go into detail, but just I want to tell you what are the essences. Well, if neutrinos have masses, neutrinos change their flavor or type from one flavor or one type to the other. For example, oscillations could occur between muon neutrinos and tau neutrinos. And if we assume neutrino oscillations between muon neutrinos and tau neutrinos, then the oscillation probability can be written here. For example, this blue line, this is the probability that nu mu to remain nu mu. And if nu mu, the probability of nu mu to remain nu mu is getting very low, at that moment, the probability of nu mu to nu tau gets high. And well, also, if nu mu propagate further, the probability come back to unity. Further, if nu mu travel further, then the probability goes down and go up and so on. So you notice that the nu mu survival probability oscillate. Therefore, we call this phenomenon as neutrino oscillations. And also, one important thing is, if neutrino mass is smaller, the oscillation length, that is the distance from, say, from here to here, gets longer. So by observing this length, we know the information. We get the information on the neutrino mass. Okay, now we published our first paper on atmospheric neutrinos in 1988. And well, unfortunately, for several years, we didn't get any supportive result. And finally, in 1991 and 1992, we get the completely consistent results from the IMB experiment, which is the another large water Cherenkov detector. anyway, although it was clear that the small mu over E ratio or nu mu over nu E ratio implied something unexpected, the physics behind this result was unknown. We recognized that the neutrino oscillation was a possibility, as we wrote in the paper. However, there are various questions. Of course, first of all, was the result due to neutrino oscillations? Even if we think so, we are not sure if the oscillation is due to nu mu to nu E or nu mu to nu tau. Of course, we are unable to exclude some other physics. So, the observation of the deficit of muon neutrinos is not enough to conclude the physics, to get the information on the physics behind them. So, what shall we do? Now, we have to think what will happen if the muon neutrino deficit is due to neutrino oscillations. Well, you can imagine. Well, first of all, this is the oscillation probability as a function of log of essentially flight distance. Then it is clear that if the flight length is short, there's no time for neutrinos to oscillate. Therefore, if this is the case, the neutrinos coming from above, that is, neutrinos produced in the upper atmosphere, have not enough time to oscillate. Therefore, nu mu's produced there should be arriving to the detector as nu mu. However, nu mu's produced in the other side of the Earth must travel long distances. Therefore, they may have enough time to oscillate. So, we thought that one of the key data to convince us or convince the community that the muon neutrino deficit is due to neutrino oscillations is to see the up-down asymmetry of the muon neutrino data. Okay, so we want to get this up-down asymmetry information. However, at this moment, I'm sorry, maybe this is too detailed. But, well, here I want to explain that we are unable to know the neutrino direction because we are only observing muons or electrons produced by neutrino interactions. Therefore, we have to know the typical scattering angle of the neutrino interactions, and this is the result of the simulation. And we realized that we have to study high energy neutrinos. So, well, unfortunately, in the previous study published in 1988, we only studied low energy neutrino events. Therefore, these events were not good enough to study the up-down asymmetry. So we decided to study higher energy neutrino events. Also here, I want to mention that the flux of the neutrinos is pretty up-down symmetric. So this also tells us that the up-down asymmetry measurement has a very robust feature. Therefore, if we have good enough statistics, we will be able to come to the conclusion. So from these considerations, we thought that we should study multi-GeV neutrino events. They are higher energy neutrino events compared with the initial study. And therefore, we started the data reduction work for, well, okay, these are, well, okay, anyway, the data reduction work for multi-GeV neutrino events approximately 1 week after the submission of the 1988 paper. Unfortunately, Kamiokande was not big enough. Well, if the neutrino energy gets higher, the flux gets lower, therefore the event rate is lower. Therefore, it took almost 6 years to get some meaningful results. And well, after 6 years, we come to this plot. This plot shows the zenith angle distribution for electron neutrino events and muon neutrino events. Here, a zenith angle is defined so that cosine theta minus 1 is neutrinos coming from the other side of the Earth. Cosine theta 1 is the neutrinos coming from above. And you can see for muon neutrino events, there is a deficit compared with the prediction or compared with the downgoing neutrino events. And the statistical significance, well, up-down ratio was 0.58, but the statistical significance was only 9.8, 9.9 sigma. So, well, although it took 6 years, we had not high enough statistics to conclude. So we concluded that we need much higher statistics. Therefore, we needed much larger detector. Now, I come to the real discovery. Well, for this discovery, as expected, we needed much larger detector. And this much larger detector is the Super-Kamiokande detector. It is a 50 kiloton water Cherenkov detector, and the fiducial mass for the physics analysis is 22.5 kilotons. That means we can observe the atmospheric neutrino events approximately 20 times faster than we were able to do in Kamiokande. And well, you can see this is the international collaboration with many countries. And in fact, the international collaboration began in 91 or 92. This was a photo we took after the initial discussion about the collaboration between USA and Japan. And here is Yoichi Totsuka, who was the spokesperson of Super-Kamiokande. And well, you can see several people from USA and several people from Japan. And here is me. Anyway, Super-Kamiokande was constructed and started taking data in April 1996. And of course, you can realize how big the detector is if you recognize 3 people on a rubber boat. In any case, this is a big detector. You may recall that I showed a photo who worked in a mine for the construction of the Kamiokande experiment. In that photo, we had only less than 10 people. Now, Super-Kamiokande is a big detector, so we cannot construct this detector with 10 people. We need more people. Yes, and this is a photo we took in the summer of '95, and this is in fact the typical number of people worked in the construction, and it took almost exactly 1 year to install the photomultiplier tubes into the Super-Kamiokande tank. Now, I said that the event rate in Super-Kamiokande is about 20 times higher. So that means we have to improve something in the data analysis as well. Actually, one of the limitations of the Kamiokande analysis was the necessity of the event scanning for all the data and Monte Carlo events due to no satisfactory fancy ring identification software. So we had to invent the new software, and actually it worked well. Well, for example, if you look at this event display, you notice 2 to 3, maybe 3 Cherenkov rings. So the first task we needed to do was to identify the number of Cherenkov rings. And in fact, this worked well. We had a new bright idea from our collaborators, and the separation of the single ring and merge ring worked well. Anyway, this is the typical event pattern observed in Super-Kamiokande. In this event, we have single Cherenkov ring, and here we have 2 Cherenkov rings. And in addition, we have other event type of events. Here in this event, a neutrino interaction occurred in the detector, but one particle exits to the outer detector and to the rock. So you can see the difference in the event pattern. Also, you can see the signal in the outer detector. Furthermore, we use these events. These are the neutrino interactions occurring in the rock below the detector, and we only observe muons produced by this interaction. So in this event pattern, you see a muon enter from the bottom of the detector and exit to the top of the detector. So we use all of these events to study neutrino properties. And well, you realize that all these events have a significantly different event topology. So in order to analyze all of these events, we needed the collaboration of many people. So I would say that the collaborative work of many, especially young people, have been essential for the discovery of neutrino oscillations. In any case, after 2 years of the operation of the Super-Kamiokande detector, we were able to do all the analysis, and we come to conclude that the data shows evidence for neutrino oscillations. And this is the transparency. And young people may not know this word. Well, about 20 years ago, people showed this kind of plastic to show their result. And well, all the detailed information were written by hand. Anyway, this is one of the most important plot shown at this meeting. And here you notice that, well, again, this is the dense angle distribution. And here is the downgoing neutrinos, and here is upward-going neutrinos, and this is for muon neutrino events. And you notice is that for downgoing neutrinos, the data which are shown by black dots are in good agreement with the simulation which is shown by these shaded squares. However, for upward-going events, there is some huge deficit. So from this data, together with the other supporting data, Super-Kamiokande concluded that the data gave evidence for neutrino oscillations. And, well, I want to mention that we were fortunate because at that time, there were two other atmospheric neutrino experiments. They were macro experiment in Italy and the Sudan 2 experiment in United States. These experiments observed the atmospheric neutrinos and confirmed neutrino oscillations. So neutrino oscillations was pretty quickly accepted by the community. Okay, now I want to mention what are the results, recent results? Well, first of all, I want to mention the data updates or statistical improvement. Okay, this is the 94 Kamiokande zenith angle distribution. Here in this plot, we had only 135 events. This is the Super-Kamiokande plot at neutrino 98. Well, at that moment, we concluded that this is due to neutrino oscillations. And here, we had 531 events. Even after that, we have been taking data, and this is the most updated Super-Kamiokande data, and the number of events plotted here is 5,485. So, well, we have more than 10 times larger statistics compared with the 98 Super-Kamiokande data. So, using these events, we are able to do various studies of neutrino oscillations. Well, one of them is the precise determination of the neutrino oscillation parameters that are the determination of the neutrino mass parameter and the mixing parameter. Well, okay, well, this is the actually copy from the 98 paper. And this is the allowed region from Super-Kamiokande on the neutrino mass parameter and the mixing parameter. Now, well, if we cut here and expand, and if we plot the presently allowed parameter region, they are shown here. So you notice that now as far as the parameter estimation is concerned, we have been improving really significantly. But, well, of course, you may notice what does this mean. Well, okay, well, I don't want to go into detail, but I want to tell you that the mass suggested from this measurement is, mass means neutrino mass, is approximately 10 million times smaller than the electron mass. So, and of course, electron is the lightest elementary particle, except for neutrinos. So, neutrinos are really, really light. Also, I want to mention this. Well, now the aroused region is sticking to the right. This is suggesting that the well, okay, I don't go into detail about the neutrino mixing, but this mixing is kind of maximum. And this is completely different from the expectation based on the quark physics. And we'd like to understand why. Of course, well, of course I don't know, and we don't know, but this is the mystery, why the neutrino mixing is so different from that of the quarks. Now, well, so far, well, I used this plot as the evidence for neutrino oscillations, because long-traveling neutrinos have disappeared. And however, we want to really confirm neutrino oscillations. Well, because, well, this is the calculated neutrino oscillation probability. However, what we observed here is just the deficit of mu neutrinos for traveling long distances. So we really wanted to observe this feature. Of course, if you want to observe all these rapid oscillations, it's very difficult. You need extremely high resolution detector. So we decided try to observe this first dip. Then that will be good enough to really convince ourselves that is due to neutrino oscillations. And in fact, we carried out the special analysis, and we in fact get the first dip. So from this observation, we conclude that the data really shows oscillations. Okay, I want to mention one more thing. Well, so far, all of our discussions were based on the deficit of muon neutrinos. However, if the muon neutrinos disappear, then at the same time, tau neutrinos should be appearing. So we should be able to observe tau neutrinos. Well, okay, that is the basic idea. However, it turned out this is extremely difficult. First of all, this is the cartoon of a nu-tau interaction. Nu-tau produces tau and then produces typically many hadrons, pions. So this is similar to other background events. And this is a typical event pattern of the nu-tau event. So, well, this is extremely difficult to tell this is nu-tau event. Anyway, we decided that although it's very difficult, we try to find some hint for the nu-tau appearance due to neutrino oscillations already in 2001. And well, it took us many years to get convincing result. And this is the Zins-angle distribution for tau-like events. Unfortunately, even if tau-like event, there are a lot of background events. And well, we have to precisely estimate the background events, and we have to get the excess to the estimated background. And finally, after more than 10 years, we get the 3.8 sigma excess over the background, and this is the evidence for nu tau appearance. Now, okay, in the remaining time, I want to briefly discuss the future. Well, okay, now, so far I have been discussing nu mu to nu tau two flavor oscillations. However, we know that there are three neutrino flavors. Therefore, we have to discuss the neutrino oscillation within the three flavor oscillation framework. And in fact, now many of the three flavor oscillation parameters have been determined, observed by various experiments. However, still, there are some unknown parameters. One is the mass hierarchy. That means we typically assume that the nu3 is the heaviest neutrino mass, but we are not sure if this is really true. Maybe this mass state could be the lightest, or there might be a difference in the oscillation probability between neutrinos and antineutrinos. And actually, this information seems to be quite important for us to understand the baryon asymmetry of the universe. So, in fact, these two are extremely important questions. Therefore, neutrino physicists are thinking about the future very seriously. And this is the, maybe the partial list for the future neutrino experiments. There are reactor experiments, atmospheric neutrino experiments, and long baseline experiments. And well, okay, maybe I don't go into detail. Maybe this is too detailed for this talk, so I skip. And one of the future experiments is the Hyper-Kamiokande experiment. It's going to be located here in Japan, in Kamioka. Well, it will be much larger detector than Super-Kamiokande. The total size of the Hyper-Kamiokande detector is assumed to be approximately 1 megaton, which is 20 times larger than Super-Kamiokande. Well, okay, this is going to be a huge project. So, well, it's really going to be huge. So, well, we have to make sure that this size, 1 megaton, is really needed. And in fact, people are thinking maybe this is a little bit too big. Anyway, in this detector, we'd like to do a long baseline experiment and the atmospheric neutrino experiment. And well, maybe these two figures are too detailed for this colloquium, but well, this experiment has a very good sensitivity to the mass hierarchy determination. That is to know if the nu3 mass state is the heaviest or lightest. Anyway, I want to tell you about the status and plan for this Hyper-Kamiokande. Now, the proto collaboration has been formed. There are 240 people from 13 countries, and R&D funds have been granted in several countries, including Japan. And also in Japan, this project has been selected as one of the top 25 top priority future projects by the Science Council of Japan in 2014. but this was not included in the next, that is our funding agency, roadmap in 2014. Therefore, we must wait for the next round, that is going to be 2017. And if the construction begins in 2018, the experiment could start in 2025. Well, okay, this is about the CP violation, but, well, again, I think too detailed. So, well, I want to go to the appendix that is coming back to the signal. I said, well, 35 years ago, the underground experiment started to search for proton decays. Well, in the course of the proton decay searches, we encountered the atom-shaped neutrino problem, and we concentrated on the atom-shaped neutrino studies. However, we have not been forgetting about the signal, that is the proton decay. Well, actually, this is the Super-Kamiokande expected sensitivity curve for these two modes. And if next generation detector is in operation sometime in 2020 then the expected sensitivity is coming to around 10 to 35 years. So, well, although we are still searching for proton decays, now we are trying to search for proton decay with the lifetime 5 orders of magnitude longer. Okay, now I will summarize. Well, the unexpected mu-neutrino deficit in the atmospheric neutrino flux was observed in Kamiokande in 1988, and subsequently, Super-Kamiokande discovered atmospheric neutrino oscillations in 1998. I feel that I have been extremely lucky because I have been involved in the excitement, well, whole excitement of this discovery from the beginning. And the discoveries of non-zero neutrino masses opened the window to study physics at a very high energy scale, clearly beyond the standard model of particle physics. And this high energy scale physics is probably related to the grand unification of elementary particle interactions. And there are still many things to be observed in neutrinos, and further studies of neutrinos might give us fundamental information for the understanding of the nature, such as the origin of the matter in the universe. Okay, that's all. Thank you very much.
Thank you, Kajita-sensei, for a very clear talk. So the scientific session is open for questions.
Thank you for your inspiring speech. My question is, which kind of altitude is most important for scientific research from your experience? Thank you.
Yeah, okay. Well, first of all, well, I didn't tell. After our first publication, people had a lot of negative opinions. Also, the results from 2 other experiments almost immediately published after the Kamiokande paper showed no such effect. However, I thought we did everything right. We had a confidence. So I decided to continue the study. So I think, well, then you may ask, what is the motivation for continuing. Well, what is the okay. Maybe we need to be a little bit optimistic. You don't want to be disturbed by negative opinions. Also, well, I have been very careful not to make any mistakes. So I have to be careful, and indeed I did. So all this optimism and carefulness, and also I was very much excited by the potential suggestion of the large mixing angle, which was not expected by the community. So I thought that this is going to be very important physics if this is right. So I also, motivated by physics, I decided to work on this. So I think all of these are important.
For experimentalists, take your background very seriously. It may be made of gold, right? So any other questions? Inami-san.
You are presently working on detection of gravitational waves.
Yes.
And in the end of the talk, you also mentioned proton decays.
Mm-hmm.
So you're working on three things at the same time. It may be very difficult to concentrate on three things at the same time. How do you handle this?
Okay, I see. Okay, well, for the future neutrino detector or Super-Kamiokande, I am helping them, but I'm not working on particular element of R&D. On the other hand, I'm spending a lot of time to help the project of the gravitational wave. That is my stance. Maybe 90% of my research time for gravitational waves, and 5% for Super-Kamiokande and 5% for Hyper-Kamiokande.
Okay, Pauchi.
How about the cosmic background of neutrino? So CMB will already observe. So the next one, cosmic background of neutrino, because they will be, according to the mass, they will be cluster. So maybe there is a lot more we can see. So do you think there is any way of doing it?
Yeah, well, detecting the cosmic neutrino background is a very important issue. However, I think we have no idea to detect them. So if you have any idea, please try. It may not be easy.
Yes, you gave a very nice talk. At the end, it's amazing actually. You can see the new town. I was just wondering, okay, you didn't go to a detail about the how to select the new town events. Is there a difference between the new? I think there are a lot of difference between the new town and the so-called the multi-GeV type events. If the one you show, I don't know how many rings in there.
Yeah.
Can you actually go a little bit detail?
Okay, well, actually, it's extremely difficult to separate neutral events and other background events. And actually, a large fraction of these background events are either new E charged current events or neutral current events. However, there are several small differences. Therefore, we use the currently most advanced technique to separate these these categories. And we are actually using the artificial neural network algorithm to separate them. Of course, however, the background is huge, signal is small. So we simply improve the signal to noise ratio, but still the noise is much bigger. Therefore, in the end, we use the Zin's angle distribution to get the tau portion, because new taus are only produced by neutrino interactions. Therefore, new taus are always upward going. So we use this feature to statistically estimate the new tau fraction.
我被提醒一下，稍微解释一下啊。刚才的问题是关于那个 tau neutrino 的产生 tau 的事件，那我想不可能详细解释了啊。那因为熊教授说这个应该相当的困难，那回答大致就是说，当然很困难的哈，用一些神经网络啊，然后这些 tau neutrino 一定是往上的等等啊。好，any further questions?
Prove that the neutrino has mass. If the neutrino has mass and it is a particle, it will move under correlation to each other. Then this will produce pressure like air pressure. I'm interested if this pressure field can be used as the medium to transmit the light.
Transmit what?
As the medium, the pressure field can be used to transmit light wave, like like similar to the sound transmit by air. In the air, we have pressure from the particle correlation. Now, in the neutrino, they also particle, and they must move and correlation to each other, and this will produce pressure. The pressure should be about 1 million times of the air pressure. How do you think if this can be a medium to transmit light?
Well, I have to calculate, but the pressure should be very small. Well, I'm thinking about the neutrinos coming from the sun, but I think the effective pressure due to neutrinos from the sun must be very small. But I'm sorry, I'm an experimentalist. Maybe I'm wrong.
刚刚问题是说这个微中子既然有质量，那它们也在运动，会不会有压力？ Well, allow me to say, even without mass, they are moving. So in principle, they have pressure, but they don't interact, so they have no pressure. A simple answer 就是说这个微中子它几乎不发生作用啊，所以跟我们平常的气体不一样，它基本上是对我们来讲是没有 pressure 的啊。So I roughly answered it for your audience. Okay. Any further questions?
Sir, it just occurred to me. I think you didn't mention the 1987A, and I think that discovery actually from Kamiokande is also very important.
Yeah.
And that's the neutrino events from the supernova, right?
Yes.
Which
yes.
may be related to his question.
I see. Sorry, I didn't mention anything about the neutrinos observed in supernova SN 1987A. Yeah, well, actually, well, okay, not scientifically. That was very important. Well, this observation suggested that the neutrino physics or neutrino observation is very important. And therefore, that observation motivated the construction of the Super-Kamiokande detector. And then, of course, we did a lot of physics with the Super-Kamiokande detector.
简短的讲，就是熊老师的 comment 是说， 在1987年的超新星爆炸是那个 Kamiokande 的那个神冈实验看到的啊。那这边不知道有没有那个星球爆炸的专家 ？I guess what you mean is that in supernova explosion there is some pressure coming from neutrinos because the number is very large,
I see,
and it matters also for the evolution of that explosion. Okay. 就是说，在超新星爆炸的时候，因为那个微中子的数量非常大，所以它也在那个爆炸的过程里面是有影响力的。所以部分回答您的问题啊。So, but it was okay to continue. 那个超新星爆炸的事件 actually led to the Nobel Prize for Toshiba Sensei. Okay, and 而且呢，刺激了那个超级神康实验的建造，就是把它增大10倍以上啊。Okay, any further questions? Especially, I would say, from students. This is your chance. He was working more or less like a student and made a discovery. So this is your chance to ask the question.
Professor, since you have worked in detecting the proton decays for more than 30 years, but the data shows that the proton decay's energy is maybe 5 orders than a spec. So do you still think that you will keep detecting the proton decays and the GUT theory, because it's kind of do you all still believe that it's a grave you will still do that, or you will just change your interest into other field?
Okay, well, first of all, we still think that the observation of proton decay is really, really important towards the deeper understanding of the elementary particle physics. Well, because this is the unambiguous indication that the 3 forces are unified. Now, of course, detecting proton decay is getting more and more difficult. Well, Super-Kamiokande is going to be a huge detector. However, if we only want to observe proton decay without any other physics, I think it is not a good idea. If you build such huge detector and get no physics, that's not a good idea. So we need to have a very convincing other program that can be carried out in Super-Kamiokande. And at the same time, we'd like to improve the search for proton decays.
好，我想so partially 的问题是说这个继续探讨那个质子衰变，是不是会继续进行下去？Allow me to say, you have already changed, right? According to a previous question, you are working on gravitational wave detection. 它其实主力是放在这个重力波侦测了，right?
In general, I'm talking about proton decay as a general physicist.
那另外他提出来是说，这个因为侦测器越做越大，如果你做一个更大的侦测器却没有发现的话，那这个也有一点为难的地方。Okay, I think we still have another session, so if you're interested to ask further questions, you're welcome to stay. 我们要进入下一阶段啊，那所以你如果有这个你觉得不那么科学的问题，欢迎留下来继续问啊。Okay, so let's have a break of 10 minutes, and let's thank Kajita Sensei again.
Thank you very much.
我首先这么讲了啊，今天不是座谈会，今天是记者会。那熊老师跟我坐在这里的话，我相信多半的问题会是用中文问的。那我们可能不管是他的回答，我们都会中介一下。不过就是拜托各位不要把它变成像是我们之间的座谈会，我想这是一个主体性的问题。Okay, so 我想记者会就开始，原则上20分钟左右。任何的提问吗？我想你们也许指定熊老师或我好了，这样比较不会跳来跳去啊。你们应该写下了很多问题吧？
好，那我们现在记者会正式开始。那不管是你的身份是媒体，或者是学生，或者是老师，那我们欢迎提出您对于教授这个专业领域有任何问题，或者是其他任何问题都可以提出来。谢谢。好，我们记者会正式开始。那有任何的问题，好，请提出来。谢谢。
直接讲。你好，三位教授好，我是联合报的记者，想说问一下教授这边，就是因为就是我们知道就是这种微中子好像被形容是蛮难找到一种鬼魅般的那种的例子啊。那想说再问一下教授说，他当初到底踏入就是一开始研究微中子的契机是什么？然后在研究的过程中有没有遇过什么样的挫折，或者是这个说数据很难找啊，或者是说就是一些挫折，或者是想要放弃的时候这样子。
Okay, I'll start. So the question is, neutrinos are ghost-like and very hard to detect. So what induced you to enter this kind of a subject? And in your studies and research, what kind of frustrations, difficulties, and so on you have encountered? Okay.
Well, okay. For us, the difficulty I felt was when we wanted to study the three-flavor neutrino oscillation effect. Well, in the talk, I only discussed nu-mu-nu-tau oscillations. However, because we have 3 neutrino flavors, the 3 neutrino mixing effect must be observed. However, well, we have been trying hard to observe this effect, but it turned out it is not easy to study this effect in Super-Kamiokande. And in fact, other dedicated experiments did much better job than we did.
我先回答一下他所讲的。我想，问题还没有，回答没有回答完呢。所以他的回答是说，这个，至少在他的实验里，他觉得主要的困难就是，因为他们讲的是这个 nu-mu 到 nu-tau 的 mixing， 可是真正想研究的是3颗不同的微中子的混合。那这个，在这个 Super-K 的实验蛮难做的，而一些其他的实验做得比较好。But let me repeat that question again. I guess the question goes back more to you, say, 20, 15 years ago, when saying that how did you turn into neutrino studies, and then along that path, what difficulties you have encountered?
Actually, well, at that time, I don't find any serious problem.
So I assume your graduate life, student life, must be very pleasant.
Yes, I enjoy the PhD student life very much.
我先解释一下啊，所以我刚刚已经转化，把问题稍微再强调一下，说是15年、18年前他在做这个题目的时候，当初怎么转过去，然后那个当时遇到一些什么困难？他可能刚从斯德哥尔摩回来嘛，那他说好像也想不大起来还是什么。那熊老师就说，那你的那个博士生涯应该是很愉快的，那他大致同意了。But now let me continue that question and ask you as part of that question. In 1988, I think I've told some of the audience that in 1988 you mentioned that IMB agreed with Kamiokande, but 2 other experiments disagreed. So you had a result which was nullified. It was not accepted. That's 1988. So it's more 18 years ago. And along the path, of course, you expressed frustration at 6 years data, and it's sort of in between. So from 1988 to 1998, I guess that I reframe that question. Try to think hard, any difficulties or frustration you had faced.
Yeah, well, okay. Well, certainly the results from the other two experiments who published the atmospheric neutrino results, which were just consistent with the expectation. Well, okay, that was not encouraging. But on the other hand, really, we didn't find any problem. So we simply thought that maybe this is the only issue of the time.
所以我刚才把问题再稍微深入一点啊，因为1988年的时候，那个 Kamiokande 的结果是指向这个微中子震荡，那一个美国的实验也认同，可是有另外2个实验是说他们没有看到那个效应，所以说那时候有没有一些困难啊、痛苦啊？那他是认为没有，因为他们说穿了就是还蛮相信自己所做的结果，所以另外一方面，我们做实验的人常常讲的就是需要时间，也就是更多的数据来证明。OK， 我想我们换一个问题好了，然后现在交给熊老师，所以。
Konnichiwa. Actually, I don't speak Japanese, so well, I have to confess that I don't understand anything about your research. So I just want to ask you some little question like, how the Nobel Prize changed your life? And my second question is that you didn't win to the best universities. You didn't win to the best universities in your life. I mean, you studied in Saitama University, right? So how do you encourage the young students in Japan and in Taiwan that how can they to pursue their academic life if they don't go to the best school?
Yeah, okay.
Thank you.
Yeah, okay, yes. The first question was already forgotten. Good. Yes.
How did Nobel change your life?
Yeah. Okay. Yes. Well, after the announcement, yes, my time is continuously stolen by someone else. Yeah, and well, I have a difficulty in serving to our institute. Also, I have a difficulty to be involved in the KAGRA experiment, which is now in a critical stage. But I have been stolen all of my time, so I have been away from KAGRA in the last 2 months. That was a problem. But I hope to come back to the previous life gradually. I don't know how gradual it will be. And the second question is, again. Oh, site. Well, there. Okay. Okay. Well, I simply recall the university that the Japanese Nobel laureates graduated, as the undergraduate. And well, I was from Saitama University, and another person who got the Nobel Prize this year for medicine is from the Yamanashi University. And the last year physics, one of them was from Tokushima University. Actually, very roughly, half of them are coming from the so-called local universities. So this suggests that if you have the interest in research or interest in nature, understanding nature, you have the chance. You don't need to worry even if you do not go to the top universities.
所以这边我大概做一下翻译啊，这个他当然拿到诺贝尔奖，这个其实大概从这个宣布之后啊，他大概就已经就相当忙了，他基本上不太容易进入这个他 过去他现在想做的这个叫做 KAGRA 这个实验呢，他几乎2个月都没有办法能够在这个实验上工作了。但是他希望慢慢能够这个回到就是说之前的这个这种生活了。那当然我们要看他下面的这个几个月的行程而决定啊。那另外就是关于就是他谈到这个不止今年除了他自己之外，对不对？还有另外一个诺贝尔奖得主，还有去年的也是物理的。那其实都不是从日本，就说最知名的这个国立大学的，他们是有些是私立大学的毕业的，但是一样 OK 都可以，就说朝着自己的兴趣去做这方面研究而有成就了。我想这是他对大家的鼓励了。那个其实念书这个最重要的还是自己的兴趣啊，有兴趣的话，其实并不在乎你的所谓出身的大学。这个出身大学，我想我只多讲一句啦。那个我本身的感觉，也许他的也是这样的，就是说那个只是也许第一步的时候踏进社会有一些帮助，其实后来并不见得有帮助。
我想刚刚熊老师用了一个字就已经是华丽掉了。这个做学问不只是念书。另外那个 Saitama University 中文是岐玉县啊，岐是玉字边，然后玉就是玉啊。有没有进一步的问题？
不好意思，我是自由时报。然后很抱歉，就是可能要再从比较基本的问题再请教一下，就是我们知道这一次诺贝尔奖是证明了微中子它具有质量，然后就是一个微中子震荡的现象。那可能它从基本上面就改变了或与过去我们在宇宙认知上面的一些基础的一些看法。这样能不能够再请那个就是韦田教授再讲一下，说就是这样的一个改变，或它对人类或对知识，就是能够有什么样更突破性的一些，就是我们要怎样去认知他们这样的改变跟发现？因为可能一般社会大众不是在这个就是天文物理学的这个领域里面，或许比较难去 touch 到这样的一个，就是说这个领域的一些深奥的部分。那可不可以就是透过我们韦田教授的一些话语，然后再帮社会大众再多多了解、多多接触这方面的神秘这样子？
你说是这个发现的后续的影响？对，
后续的影响，对，因为它就是从根本上改变了我们对宇宙的认知这样子。那是否可以再多解释一下这样子
？Can you explain and give a perspective further on the impact of this neutrino oscillation discovery, both in terms of fundamental science or towards our understanding of the universe?
Okay, well, as I discussed at the talk, the neutrino mass is extraordinarily small, and well, 3 years ago, there was a Nobel Prize to the Higgs mechanism, and you may, well, that is the mechanism to give the masses to particles. However, neutrino masses are just too small to be generated by the same mechanism. So we think that there must be other physics to generate these small neutrino masses. And in fact, in general, in order to generate small neutrino masses, you typically need very high energy, well, high mass scale physics. So we think that the small neutrino masses are related to the extremely high energy scale. And on the other hand, well, as I mentioned in the talk, there are theories called grand unified theories, and these theories predict that the forces, elementary particle forces, are unified in the extremely high energy scale. And surprisingly, maybe the physics that the small neutrino masses suggest and the grand unified theories suggest may be directly related. So that means neutrino masses could be one of the hint toward the understanding of the unified theory of elementary particles. That is one thing. Then now we look at the universe. Well, we know that the universe was, difficult to say. Well, there was a era called inflation. After that, the hot Big Bang universe was born, and then since then, the universe has been cooling down. And at the very hot Big Bang stage, the number of matter particles and number of antimatter particles should have been essentially equal. But, while the universe cooled down to the present temperature, somehow only a fraction of the particles remained in this universe. This is a big mystery. And well, so far, the only reasonably accepted scenario uses small neutrino masses. And well, if I go into further detail, it will be a little bit tough.
OK， 那个所以在基础物理方面呢，那个微中子质量虽然存在，可是非常低。所以2年前那个希格斯那个跟安格列的诺贝尔奖，基本上是给说质量怎么产生的。那这边为什么会超越标准模型，就是因为这个质量实在太小，可是它存在，所以大概有在我们现在的粒子物理标准模型之外的额外的物理，要来解释为什么微中子质量这么的低。那所以这个就已经是就说是基础物理了啊。那然后他其实在他演讲里面也提到说，包括他原来质子衰变的出发点，就是大家可能听过的大统一场论啊。哦对了，关联是说微中子质量非常的低，普遍认为是说根源大概是在很高质量、很高能量尺度的新的现象。那所以这个就关联到那个大统一场论。所以很有趣的就是说，他从大统一场论的追究，发现了这个微中子震荡，发现微中子有很轻的质量，说不定最后是连接回到大统一场论啊。那那第二个回答比较更关乎宇宙的是说，从宇宙大爆炸以来，大家大概也听过的，就是只剩下的粒子非常少量的粒子，可是反粒子都消失不见了。那现在一个蛮主流的一个解释，就是这个可能还是多少跟微中子质量跟它这么轻，跟前面讲的那一套关联可能是关联在一起的。我带他多讲一句了，他后来那些部分都跳过了，就是在微中子震荡这些研究里面，也去可以探讨所谓 CP 破坏了哈。不过这是将来的事情，只是说如果因为I'll add one thing first in English. I think neutrino physics has been totally amazing with all these large mixing angles. So I was mentioning already, you heard CP phase. If in neutrino physics, after Sensei's effort, after a few more decades, maybe just 1 decade, if we really find CP phase and reveal even more things, I think for the universe, the disappearance of antimatter is extremely important. OK， 所以我把刚刚的东西再简洁的中文讲一下啊。现在微中子震荡，刚刚讲说有3颗在那边互相混合，那这个混合里面跟夸克也类似，有 CP 破坏相较。那这个研究真的是做得很辉煌，所以不是没有可能在未来10年或再长一点的时间，假定发现这个事情可以解释宇宙为什么反物质消失了。我想这个不是所有可能的回答，我们就把这个问题就停在这里。 还有别的问题吗 ？Okay, over there.
Professor Kajita, it's a great honor to ask you a question here. I'm a graduate student in engineering, and my question is, when did you decide to become a physicist, and why?
I see. Okay. Well, when I enter into the undergraduate course, I already decided to learn physics, but I have not decided to be a physicist at that moment. Anyway, during the undergraduate studies, I found that physics to be interesting. So I decided to learn more in graduate course, and then I enter into I joined to the Professor Koshiba's group. And as I discussed today, the Kamiokande experiment was really fantastic to the graduate course students. We had a lot of interesting things, and we really enjoyed the experiment. I enjoyed the data analysis as well. So during the graduate course studies, maybe in the early PhD period, I decided to be a physicist. So because of the say, Kamiokande, which is so interesting to me, I decided to be a physicist.
OK， 就是刚刚是工学院的这个同学问这个问题，就是他什么时候就说决定要做这个物理学家了啊？他的回答是这样说：他其实之前是对物理有兴趣，那尤其到了大学 college 的时候。他觉得物理应该是很有兴趣，那他一直等到他到做研究生进了这个Koshiba先生的那个组的时候，那他才真正的觉得这个物理是真的是他可以做的，所以他一直到了 graduate 刚刚讲了这个研究生之后这个才真正决定他要做这个物理学家了，但是这样的回答的当然他毕业之后，尤其这个。后面这个Kamiokande的这个神纲的实验，后面还有这个我们叫做超级神纲那这后面有一系列的这个我相信这个发展，那基本上就是说他就从此就投入进来了。
I ask you, how about wanting to be Dr. Ochanomizu?
Okay, I know that in the Japanese mass media this is widely written, but I myself does not remember this fact. That was the information from my parents, so that is my answer.
But that was the atomic thing? What was the story, actually?
Yeah, actually, this was about the present-day robot.
Robot, OK. 这个也不是抢版面因为我自己读到一点我刚就问他说讲得太冠冕堂皇嘛，对不对？那读到说他好像小时候曾经很迷那个原子小金刚还是什么的，那想当这个御茶之水博士。那我就顺着刚才的问题问了，不，这一种应该还算正常的，我们都有了这个不会回答说因此我就成为物理学家嘛。I said usually just wanting to be, the robot man, whatever, does not turn you into a physicist.
Right.
Okay. 继续的问题。
老师您好，我是中央社的记者。那我想请问一下尾田老师，就是每个学者可能身上都有不同的一些特质，然后可能导致他们可以最后得到很好的研究发展，甚至成功。那想请问尾田老师，认为自己个性上有什么样的特质？比如说有的老师可能是热情，有的是好奇，有的是疯狂，有的是坚决。那不知道尾田老师的特质是什么？那还有可以给就是未来有兴趣从事科学教育的学生一些建议，或是提点他们应该从哪一些方向去着手，或是说应该注重哪一些部分这样子。谢谢。
Okay, so in viewing yourself, what personal qualities you see in yourself that made you who you are today, in terms of your studies? And then, on that basis, is there any advice or suggestion, recommendations to students of how they should, pick their field, go on with their career, and so on?
Okay, well, okay, difficult to say. I think I'm a little bit optimistic. Yeah. And at the same time, well, I have been involved in the atmospheric neutrino studies for almost 20 years. And this was clearly motivated by physics. And so I think if one wants to be a scientist, you have to have a strong interest in nature. Otherwise, you cannot continue working for 20 years for the same thing.
Only optimistic? Anything else you want to mention? I think the lady said things like, I can't fully remember, but
for example, you really love, this kind of science, the passion,
Yeah, passion, yes, but passion is is motivated by physics.
好，我试着回答一下。他其实就个人素质的回答，只强调了那个乐观啊。那我们刚才提醒一个说，譬如说很热情，然后就回到他第二个问题的回答了。他说他在这个大气微中子研究了差不多20年。那之所以能够持续，就是要对那个研究的议题本身有以及不只是那个议题，就是对研究自然界有真实的兴趣，否则是不可能维持这么长久的时间的。那所以包括热情也是一样，因为你有真实的兴趣。我想如果我们串起来刚才第二阶段的回答。好
maybe I ask a little bit more on this part because you never mentioned, which I knew, it's a Super K. I think had this disaster.
Yeah. Yes.
So there are a lot of those big photo tubes they broken down because the one of the broken shockwave.
Yeah.
So I don't know. That's a setback. But what was your feeling? Okay, what was the collaboration feeling that time? Because during that kind of the accident.
Yeah. Okay. Yes, that was the moment. All of the collaboration members were deeply depressed. And honestly speaking, I think most of the collaborators had a kind of pessimistic feeling that means the experiment is over. Actually, I think we were quite lucky because the leader had a strong mind. Well, the leader, Professor Totsuka, he had a strong mind, and on the next day, when he returned from from Canada, I don't know, I don't remember where, but anyway, after he come back to Japan, he interviewed several of us and decided to rebuild the detector without consulting any other outsiders, including funding agencies. So anyway, this decision was made and this was announced to the world with the internet. So, so with this leadership, the whole collaboration decided to rebuild, to work toward the rebuilding. So, that was the worst moment for us, but we were lucky because of the good leader.
你要翻译一下。
我刚刚其实问了一个问题啊，就是在这个超级神冈在这个建好之后，那开始在这个取数据，其实发生了一件这个惨状的 事件呢，就是他们其中一个那个就是刚刚的光电倍增管，他们在维修的时候，在水下面等于是爆掉之后就是我们叫做这个 shock wave， 它就让旁边很多的底下的通通都受损。所以我刚刚问他说，这件事情当然对他们实验室当初是一个很大的一个震惊。那他们的想法是什么？他们的感受是什么？那他告诉我了，就是说他们当时的当然整个就是说 collaboration， 就是他们的合作组的话，其实大家都知道这件事之后相当悲观了啊。那认为可能这个实验就结束了，因为要就說全部去更換的話是相當花錢花時間的一件事情。可是他說當時是 Tosuka 這個先生，他從加拿大回來，他說這個然後知道這件事情，他就跟他們座談之後，談了之後，他有基本上就說他的他是非常有這個 strong will， 他就決定是說一定要把它修復。那而且他做這個決定，他們開完會做這個決定的時候，甚至沒有跟這個類似像我們國科會啦，這個政府做討論，他就決定是我一定要把它做到。當然事後才去申請經費等等，那也就把整個合作組重新就又把它拉回來。大家大概後來可能開了會再決定說一定要修復。他們事實上花了蠻長一段時間修復，也非常我們局外人來看的話我知道這件事，其實是非常佩服他們能夠把這件事做到，然後真正把它修復，然後現在又重新在這個進行這樣的實驗。
Hello, Professor. I am a master's student in theoretical physics, and my question is that in recent years, I've observed that there's been a decline in funding for research and studentships in fundamental physics, fundamental research, and research that has no obvious industrial or commercial applications. I'd like to ask what you feel about this, and what kind of advice can you give to students of pure science who are looking for opportunities for research in academia or employment in industry?
In industry?
Or in the employment sector? I'm not sure.
Okay.
I think he basically says because he observed the decline in the research support recently, and what kind, your advice to the students, okay, if they want to continue the so-called the fundamental researches.
Yeah, well, this is a very difficult question. However, well, the researches in fundamental science is extremely interesting if you are involved deeply. So, although it is true that our circumstances may not be so good, but there are still many interesting things expected to be observed or discovered. So, if you are really interested in science, you could try. And also, at the same time, I want to say that the good students, good PhD students who are trained in the natural science are typically also good in various industries as well. So I think you do not need to worry too much.
刚刚是一位硕士班学生呢，这个问的问题啦，就是关于说这个好像最近近年来的话，对于这种基础研究的 科学上的这种基础研究的这种经费等等呢，好像都有这个下降的趋势啊。那当然是问他说，对于这个对这方面有兴趣的学生的话，有什么样的建议？那这个他的回答是这样子，对于这个基础研究，基本上他认为基础研究是因为有刚刚讲说有这种新发现的这种可能性，所以一直有非常有就说应该是有非常有这种有兴趣的，有那种值得去做的这种方向了。所以基本上是还是要看大家的兴趣，第一点。那第二点是所有的这些就说做基础研究，其实我们在这个经历的过程中的时候，其实我们会学到很多这种不同的技术啊，他没有特别讲里面，譬如说他之前做这个分析，对不对？这个分析的技术其实有很多应用性。那因此在你毕业之后，其实你不用担心你假如即使你觉得你不能够做到将来不能够继续做这个研究，你还是你有这个能力你有这个技术，你可以到这个业界去。业界其实很需要这方面的
还没有问题。Oh, okay, sure.
Well, I just want to say one example. Well, in the Department of Physics at the Tokyo University, we have recently started the program to encourage the PhD students to learn not only your research, but also to experience something else. For example, one student may go to an industry for say short period, maybe 1 month or so, and well, during these broader experiences, they realize that their future is not completely concentrated on not only on pure science, but also there are various ways. So, well, with this program, they seems to know that also the company or industry seems to realize that these pure science students are extremely, useful is not a good word, how to say.
I think they learn fast.
Yeah, they learn fast. They are extremely intelligent, and they are could be an extremely good ingredient to these companies. So I think this kind of exchange, information exchange program, basically, is a very important program for the future of the students working in the fundamental science.
OK， 所以他刚刚当然要补充一下，就是关于这个东京大学，其实最近几年有一个新的这种program， 这种也就是让做这些在实验室里面或者在做这种比较这种fundamental 的这种基本基础物理的研究的话，那他们可以到业界他通常说大概可能1个月左右的这种我们叫 internship， 对不对？在那边去实习，让他们可以去看看外面是长什么样。也许他的兴趣并不是只有在刚刚讲的基础物理上，但而且也让这些业界了解到这些来的学生呢虽然他们之前念的不是比如说工程等等，但是他们确实是非常，就是说他们可以带来为业界其实可以带来一些新的想法尤其在业界其实有很多，其实我相信做研发方面的，他们是需要这种学生将来毕业之后说不定可以在这方面帮他们的公司有更好的这个发展。这是他的回答。
As an experimentalist, how important do you think it is to know the frontier development of theory?
Difficult question. Well, yeah, well, This is my problem. I'm not catching up the recent theories. Okay, that's all.
But he's asking how important.
Yeah. Well, okay, but of course you do not need to follow the various details of the theories, but you need to know the fundamentals of the theories. Otherwise, you have no idea what you are doing.
所以作为问题是说，作为实验家要怎么追逐，还是跟上，还是知道那个理论的前沿呢？我想尾田先生所说的是说，容我讲，其实是不需要。没那么真。他知道的有限啊。那基本的回答说，你要知道一些基础的事情。所以我如果反映他刚才你看到他的手势了，他没有办法真正回答你的问题。所以may I add that usually, well, you do need to know something, but for instance, I don't think you studied neutrino oscillations because you wanted to study neutrino oscillations. You discovered, and then there's theory corresponding to it. Would you agree? So may I use that as a partial answer? Okay, you want to say something?
Yeah. Well, okay. Well, as an example, neutrino oscillations. Well, of course, before starting serious about the data, atmospheric neutrino data, we knew that neutrinos should oscillate if they have masses. And well, so it is clear that we need to know really the fundamentals of the theory predictions. But on the other hand, there are various variety of theories. For experimentalists, I think it's just not necessary to follow all of them.
OK， 看微中子震荡的部分啊，我就不翻译我刚才那个回问他的啊。他的微中子震荡，那个他们事前当然就知道说微中子之间可以震荡，可以混合，那所以这就是算是一种基础知识了啊。那可是理论的话有很多不同的层次，那你不需要都知道，不需要那么深入。好，最后机会 ，last question. But you already asked one. Okay, so go ahead.
他跟他的恩师小柴昌俊就是彼此的互动，那恩师对他的意义又是什么？那一门有2个诺贝尔学者，那他们就是之间的互动。
你刚也不是用英文问的吗？都没中文。So the question is about your personal relations with Koshiba Sensei, and since from the same group. There are now 2 Nobel laureates. Whether you have any comments on that?
Well, okay, yes. Well, I simply want to say I was extremely lucky. The Super-Kamiokande was initially proposed. Idea was proposed by Professor Koshiba, and we thought that this is a good idea. So we worked hard to realize the experiment. So, well, actually, without Professor Koshiba, I don't know where I am now.
Any personal contacts?
Personal contact. Well, okay, yes. In fact, Professor Koshiba was extremely, say, good person to encourage students to think fundamentally important things. And also, he was, well, not also. I want to tell what he was always telling us. He always told us that we have to think what we should do after, say, after getting PhD or after getting the faculty position. You need to have your own experiment, and this own experiment needs to be of fundamental importance. He's always saying something like that. So, therefore, we have been naturally thinking to this direction, and that clearly helped me to study neutrino oscillations.
熊一鸟试着翻译吗？
他当然跟他的老师这个小柴昌俊，中间谈到他们之间的互动了哈。那最重要就是那个小柴先生的话，他一直鼓励他们啊，就是要多想啊重要的这些的问题，然后尤其是应该是他们可能是不管是要毕业了之后或毕业之后到，譬如说到了做那个到学校做老师好了，那一定要有自己的这种的计划的这种的方向，那一定要是很重要的这个方向的话，那才值得去做。这样是对他们的这种教导的鼓励。我不知道还有没有补充。
前半段是说这个整个神冈实验、超级神冈实验都是小柴教授所发动的。那包括刚刚熊老师讲的，鼓动学生们要想最基础的问题。不过他等于你刚看他的手势的，就是说如果没有小柴先生发动这么好的实验，他也不知道他会在哪里啊。所以我想这个机运，我们大家都知道的是大过其他一切啊。当然不可能只靠机运。OK， 我想好吧，最后的问题了啊。
Tozuka also talk about the Professor Tozuka.
你说什么？
谈一谈那个副总教授。
刚不就在谈吗？你说你前面几个字没有进到麦克风里，所以你再讲一次吧。
可以就聊一下那个副总杨二教授，就是那个，对。
Could you comment on Totsuka Sensei? In a similar way.
Okay, yeah. Well, as I said, Professor Koshiba is kind of, not said, but kind of emperor. He only tells us only fundamental things. But in order to do experiment, you need to know experiment. And I learned everything from Professor Totsuka. And since then, I have been learning everything from him. So, Professor Totsuka is clearly another my advisor.
他是说这个小柴先生就像皇帝一样啊，一直发号施令吧，就讲说你们要做基础研究啊。可是也讲说你一定要学会做实验嘛，叫学会做实验。那他是说他的一切的那个实验的经验知识都是从副总先生学的啊。那副总先生就像是他的另外一位老师的师傅了。好，我想我们今天这个记者会就到这里啊，谢谢大家的踊跃。